Okay, so thank you very much, everyone, for coming again to this second week. And I'm glad that you have been able to preserve and be patient for the first few lectures. And hopefully, I have been able to have some practice. I have also uploaded some exercise problems, very few, that you can start doing along with the lectures. So hopefully by the end of the next week, you should be able to do all of them. And I also uploaded a list of resources. There are a lot of links because some people ask for some books and some references. So there are plenty of references for all the way from blogs and videos to books and articles and conferences. So that I think is a pretty good list maintained by and added by a lot of people. And apologies for missing out the lecture yesterday. We'll arrange a makeup class for that after the next week. So we can work out a time and date that you're all available. Okay, so coming to today's lecture. So today we are going to get started with the analyzing and building simple algorithms that also will show you how quantum algorithms and quantum computers work and how they are different in terms of thinking from classical algorithms. And we will also be able to see how to work out the outputs for given inputs for an algorithm. And also I will be discussing the programming and an actual quantum computer today. I have already shared the notebooks with you, so you can follow along once we reach that point. Okay, so any question or comment before we start? Okay, so if not, let me begin by sharing my screen. All right. Okay, so today we will sorry, the pen is acting up. Thank you for your patience. I have been able to borrow the pen from my neighbor. So let me start and go back to the journal because it's the trouble with the pen and not software. I'm going to start lecture number 4. And our main focus today is going to be on Dietz-Jozsa algorithm and Bernstein-Vazirani algorithms. So the importance of these two algorithms is that they are extremely simple and they do a task that is perhaps not very practical, and it's very hard to think of any practical use for those algorithms, but they show the advantage of quantum computers over classical computers right away. The second advantage of starting with these two algorithms is this, that they are simple and they sort of encompass a lot of the ingredients of a more complicated algorithm, and the skill that we will develop by analyzing these algorithms, it will be extremely important in analyzing other algorithms that we will study in this course, and in general you will study about quantum computers. So these algorithms are very powerful in terms of pedagogy, that they tell us how to analyze algorithms, and they also show us the advantage of quantum computers. And also there is another thing very important about these algorithms that, and I would like you to pay your attention to that, even if you don't get all the calculations right away. And that is that how quantum algorithms work, how they are different from classical algorithms, and what is the way to think about them, how do they work. So hopefully these calculations will show you that how quantum algorithms are different from the classical ones. So let's start with Dietz Jozsa algorithm, which actually solves the Dietz problem that he proposed, and he also proposed a single qubit circuit for that, and then Jozsa extended that circuit to multi-qubit as well. So the problem is this Dietz problem, that if you have a function f of x and there is some black box that can compute this function, and there are only two possibilities for this function. It's either a constant, and remember, we are going to be only working with the binary system. So all functions are on the binary inputs and all outputs are binary outputs. So a constant means that the function is always either a 0 or its output is always 1. So that's the property of this function, that this is either a constant. It doesn't matter if it is 0 or 1, but it's a constant, and or it is a balanced function. So let me show what does it mean. So a constant function means that for all the inputs, for example, it's a 2-bit function that we're talking about. If our x is 2-bit, so input either 0 0 or 0 1 or 1 0 or 1 1, the output is either throughout 1 for all input, or it could be 0. Okay, either this. So either it is 0 for all possible inputs, or it is 1 for all possible inputs. So this is a constant function. A balanced function is the one that is like this, that for half of the inputs, possible inputs, it gives 0, and for the other half it gives 1. So for example, this one, a function that gives 0 0 output for these two input, and then 1 output for these two inputs, it's a balance. Another balanced function could be that give 1 for this, give 0 for this, give 1 for this, and give 0 for this. Another balanced function could be the one that give 1 for this, let's say 0 for this, and 0 for this, and 1. The order doesn't matter. The order could be anything. It could be either the first half or the last half, or any mixer. The only requirement is this, that for half of the inputs, the output is 0, and for the other half, the output is 1. So this is a balanced function. So the problem is that if you have an access to a black box which implements this function, how many queries to that black box you need to be able to find out if the function is balanced or if the function is constant. So problem is, how many queries to find f of x. So let's first see the classical solution. So classically, we have only this choice, that this is our black box, which implements this function f, and let's say it has 3 inputs. So it has 1 output. So we first perhaps give it input 0 0 and record our output. Then we give input 0 0 1, then record our output. Then perhaps we give another input, and so on. So we keep on giving different inputs and record our outputs. And if we are just continuing to get 0, 0, 0, 0, or maybe we are continuing to get 1, 1, 1, so we can start thinking that maybe it's a balanced function, it's a constant function. But we will have to make at least n by 2 plus 1 queries, where n is 2 power n. N is the number of bits that are used for input. So total possible combinations for input are 2 power n. So it means we have to give at least n by 2 plus 1 queries to this black box to be able to see that it is a balanced or a constant function. Because when we give it n by 2 inputs, and we are all just getting 0, 0, 0, we still can't be sure, because when we give one query after half of the input, and we either get a flipped output or we get the same output, then we can say, okay, this is a balanced or this is a constant function. So let me pause here and see if everybody understands what the problem is and why classically it needs at least n by 2 plus 1 queries.
Assalamu alaikum, sir.
Walaikum salam.
Sir, a slight question. If we get constant output for n by 2 plus 1 queries, it does say, can we say it for certainty that it's a constant function if we're getting a same input? Because for constant function, we need to have the same input output for all inputs, not for n by 2 plus 1 queries.
Okay, so yeah, thank you very much for the question. So remember, we have made a restriction on the black box. We say that the black box for sure either implements a constant function or a balanced one, not any other function. So if it is a balanced function, then for half of the input, if I'm still getting 0, 0, 0, then for more than half, so let's say there are 8 possible inputs if small n is 3. So for 4 inputs, if I'm getting 0, 0, 0 as output, for the 5th one, I must get another, let's say 1 output if it is a balanced. If I still get 0, it means it's going to be a constant. So if we had said that it could be any function f of x and we have to guess it, then of course we will need even more than n by 2 plus 1, because it could be some other function other than constant and balanced. But if it has to be balanced, it can't have the same input output for more than half of the inputs. So that's why for n, just after n by 2 plus 1 queries, we should be able to see if it is a constant or a balanced. Is it okay, Madhiya?
Yes, sir. Thank you so much.
Okay. So let's now see the quantum computer solution. And for that, I am first going to, just give you the circuit, that this is the algorithm, and then I will show in this lecture that why this algorithm works and what are its different parts, and hopefully you will have an understanding after that. So we say that, let's say there is a function, a black box function, which is implemented in some other box, which we will call oracle. So in this oracle, there is this f of x that is being implemented. And this oracle works in such a way that whatever is the input of this oracle, it just multiplies -1 power f of x with the input and give the output. So if the input is some x state, it multiplies -1 raised to power f of x and gives at the output. So I'll explain much more about this oracle in just a way. So this is an oracle, and to this oracle we give inputs from our circuit such that we initialize our qubits to 0 states, and then we perform Hadamard transformation to each of our qubits, and then whatever is the output, we pass it through this oracle, and this oracle multiplies the input with -1 power f of x and then gives it at the output, and then we perform the Hadamard transform on each of the qubit again, and then we give it at the output, and then we perform measurements. So after measurement, I'm putting 2 lines to indicate that it's a classical information. So based on this measurement results, I will be able to tell if this f of x is constant or if it is a balanced. And we will see that we will be able to tell this with just single query, with just single pass of input to this oracle and also to this function. We will be able to tell whether this f of x is constant or balanced. So let me start on each of these blocks one by one. So there's one important thing in this algorithm. The first part is this Hadamard transform on each qubits, and then there is this oracle that we have introduced, and then again Hadamard. So this is the same thing, and then oracle. So I will first analyze how the Hadamard transform works, and then I will also analyze the oracle and tell you how to work out the input-output relations for different oracles, and then we should be able to understand this algorithm, that how it works. So let's start with what we call the Hadamard transform. So this is this thing. And let me work it out for general input, not just for 0, 0 input. And for 0, 0 input, we should be able to see. So suppose at the input, we have qubits, n qubits, initialized to some state x0, x1, up to xn minus 1. And then we perform Hadamard, and we get some output y0, y1, all the way to yn minus 1. So let's work out a relationship of these inputs and outputs. But before I do, let me just perhaps do a quick example before I work out the general math. So if you have just a single qubit input, then I hope that you can recall from the property of the Hadamard gate that if x0 is 0, what would be y0? Y0 is 1 over under 2, 0 plus 1. And if x0 is 1, then y1 is 1 over under 2, 0 minus 1. So Hadamard gate just, transform 0 to plus state and 1 to 0 minus 1 state. So let's take another example. So another example would be, let's say we have 2 qubit circuit. So suppose if the input is 0, 0, so what would be output? So it means this is 0, this is 0. So output y0, y1, this I can write simply as output y0 tensor output y1. So if this is 0, output y0 should be 1 over under root 2, 0 plus 1. And if this is 0, the output should be 1 over under root 2, 0 plus 1. So you can write it like this: 1 over 2, 0 into 0 is 0, 0, 0 into 1 is 0, 1, 1, 0, 1, 1. So this output state of 2 Hadamard gate is this 0, 0, 0, 1, 1, 0, 1, 1. So if you look at it, this is a superposition state of all 4 possible computational basis states with equal weight. So it means we can say that the Hadamard gates performed on all qubits just transform the system from one state to a state which is a uniform superposition of all possible states. So similarly, if for example the input would have been 0, 1, okay, so what we would have gotten at the output y0, y1, this would be 1 over under root 2, 0 plus 1 tensor 1 over 2, 0 minus 1. So this becomes 1 over 2, 0, 0, 1, 0, minus 1, 0, minus 1. So this is still a uniform superposition state with still equal amplitudes for equal magnitudes of amplitude, which means probabilities are still equal for all possible state to be present at the output. Only there are phases as well because of the minus sign. So essentially, when we have a general input state over here, what it does after this output, that at the output we get a state which is the superposition of all possible states with equal probability. The amplitudes could be different by plus minus sign, etc., but the probabilities of all states are equal. So that's why this Hadamard transform is ubiquitous in quantum computing, because it is used to prepare superposition states that contain all possible combinations of the inputs. Okay, so let's now go to the general treatment. So in general, what I can see is this. Let me just also introduce the symbolism that is used. So in general, so we can say that x naught, x1, all the way to xn minus 1, y naught, y1, yn minus 1. So I can write it in symbolic form like this, which means that there is n bit state x, and we act on it with n Hadamard gates, and we get an n bit output state. And symbolically, it means this. And this can be written like this as well. That's Hadamard on x naught, Hadamard on x1, all the way to Hadamard on xn minus 1. By the way, some people would write y naught on the right side and yn minus 1 on the leftmost side. So there are two conventions for this. Okay, so let's see how we can simplify it. So when I write this y, this really means that it is this bit string. And when we write this Hadamard with star n, then it means that Hadamard on each individual bit. By the way, some people would simply write it like this, and this would still mean that this is a Hadamard on each one of the individual qubit. This is just a compressed notation that some people use, to confuse people. Anyway, so let's now write this y again, and this h x naught, I can write it like this: 1 over under root 2, 0 plus minus 1 power x naught, 1, tensor 1 over under root 2, and this hx naught is 0 plus minus 1 power x1, tensor so on, tensor 1 over under root 2, 0 plus minus 1 power xn minus 1. And why? How can I write this? You see, when this x naught is 0, I should get 0 plus 1 state, which is the plus state. And when this x naught is 1, I should get 0 minus state. So this is just a compact way of writing that output is plus state when x naught is 0 and output is minus state when x naught is 1. Everybody's okay with this thing? Okay, so I will take the silence for yes, and let's now see. So we have n bits, so I can combine these square roots separately. So this becomes 1 over 2 power n square root. And now I can write this part in a bit more compressed notation. Let me introduce this variable k naught, which goes from 0 to 1, and I can write it like this: minus 1 power k naught x naught k naught. And how can I write it? You see, this sum means that this k naught should first take value 0. So when k naught is 0, the first term in this sum is this 0 state, and its sign is plus. So I will get minus 1 power 0. So minus 1 power 0 is just this 0. So because this is 1, So I get this 0. So when k naught is 1, this coefficient will become minus 1 power x naught. So this is minus 1 power x naught. Similarly, I can compress the next term by introducing another variable k1, which also goes from 0 to 1. And I can write it minus 1 power k naught x1 into x1. Similarly, all the way to the nth state, we can introduce variable kn minus 1, which also goes from 0 to 1. And I can write minus 1 power k naught and minus 1, x and minus 1, k and minus 1. So now I can combine all of these things together, and I can write it like this. So first sum on k naught, then sum on k1, sum over k2, all the way sum over kn minus 1. And these coefficients, I can combine them all, minus 1 power k naught x naught, k1 x1, all the way to kn minus 1 x and minus 1. And the states I can also combine, k naught, k1, all the power to the kn minus 1. Remember, this is a complex notation that we have introduced for tensor product, that k naught, k1, etc. actually means k naught tensor k1, tensor k2, etc. So let's now introduce another compressed notation, because this will be helpful for later on, because we will be using this Hadamard transform again and again. So these compressed notations will make our life easier. So I can write just this sum over k. This sum over k really means sum over k naught, k1, k2, etc. minus 1. And this k naught x naught plus k1 x1 and so on is nothing, but I can write it like k dot x, that this is a dot product between k vector and x vector, where k is k naught k1 and x is x naught x1 and so on. And this k, I can just write it like this. Some people wouldn't actually even write this vector symbol over it, so this would just be written like this. So I'm introducing this notation because when you will see the quantum computing literature, that's how you will see. So this output y, which is nothing but Hadamard on each bit of input x, can be written like this. And this is very important. Okay. And this really means the same thing that I was showing in examples. Okay. That you are summing over all possible combinations of k, and the signs in front of these different states would be given by this product k dot x, where x comes from the input. So for example, if x is your 0 state, which is going to be the case often, then this is nothing but 1 over 2n sum over k, and this x is 0, so 0 into k is 0, so minus 1 power 0 is 1, so I can eliminate this, so this becomes this. So it means that Hadamard transform of the 0 state is the uniform superposition with all amplitude plus 1. So in general, the amplitudes could be with some with minus sign, some with plus sign, but for 0 input and Hadamard, the all amplitudes are plus 1. So this is how we can work out the Hadamard transform that we will use for the Diaz-Jozsa subsets. Any question or confusion regarding this? Okay, if not, let me now move on to the oracle. So oracle is a black box device for now, which implements some functionality. Okay, and we need oracles for analyzing algorithms. And the reason for that is that there are a lot of problems that are similar in nature, but and instead of treating them each one one by one, we can relegate the differences into some black box, which is sort of trivial to that overall algorithm. For example, if we talk about the Diaz-Jozsa problem, there can be 20 different perhaps forms for building a balanced oracle, balanced function f of x for, let's say, 4-bit inputs. because you can have either first half 0, second half 1, or you can have first half 1, second half 0, or you can have 2 input 0, the other 2 outputs 1, and so on. So there are different, so all of those differences can be grouped into an oracle. And also, let's say if you talk about the search problem, so you see, building a search algorithm is usually the same thing, but for actual application, there could be differences. For example, you might be searching through names, or you might be searching through numbers, or you might be searching through other strings, and so on. But the overall algorithm that works for searching, that is almost the same. We can think about of a same algorithm for all of these problems. There could be minor differences. Okay, how do we decide that my solution is this name in this list of names, or maybe this number in list of numbers, and so on. So these minor details, we can all group them into a black box, which is incidental to this algorithm, and the detail of the implementation is going to be for a given problem. For example, after this lecture, when I'll be talking about the implementation of this algorithm, I will present one such oracle, but there are other oracles that you can build to implement different functionality. So an oracle in general, you can think of as a device that, let's say, take n inputs that are called working inputs, and let's say there is some input x, and then there could be some m inputs for ancillary functions that are just required for working of the oracle, but they may not be needed for the overall algorithm. So in general, we have two sets of inputs, and there is some, let's say, black box, we can call it OF. So this oracle which implements this function f perhaps works in this way, that let's say this x input is achieved at the output as it is, and then we can target this y input and convert into a function like this. So we implement this oracle in such a way that the x inputs go out to the outputs as it is, but the y inputs, they are XORed with the function f of x. So with this way, if f of x is 0, if you if the y is 0, if you tie this inputs to 0 0 0, which means that y is 0, if y is 0, then this output state is nothing but f of x, because when I add 0 to any bit modulo 2, for example, 0 plus 0 is 0, and 0 plus 1 modulo 2 is 1. So when you add this 0 to anything, you essentially get this thing to the output. So if this y is 0, when it is XORed with f of x, we get f of x. Similarly, you can set y is equal to 1, and then you will get something else. So let's imagine we implement an oracle like this, and this is not the only choice. You can perhaps work out oracles in different ways as well. The only thing that we have to keep in mind for quantum computers is that number of inputs and number of outputs of the oracle should be the same, so that it remains a reversible implementation, so that every evolution is a unitary evolution, and we can implement it using a quantum computer where all evolutions are unitary. That preserves probabilities. Okay, so this is a general oracle that I was talking about, and I now want to build a special oracle which is called a phase oracle. So you can call actually this oracle an amplitude oracle, because the function f of x that has been implemented can be obtained at the output just as f of x. Okay, but instead of this, in many quantum algorithms, we can build algorithms with work with the phase oracle instead of the amplitude oracle, and it's very easy to construct the phased oracle. So let's say you have an amplitude oracle with n input, and then the m bits are only 1. So I'm working with m is equal to 1, and let's say this is my input, and then this is some amplitude oracle. So what it will do, that this x goes to the output. But what would be here? If this is an amplitude oracle, we will get y plus f of x. So this f of x is one bit output. So this f of x that we are going to find out, this goes from 0, 1, n bit input containing 0, 1 to just 0, 1. So for example, this is a function that takes as input an n bit string of 0, 1s and gives at output only one bit of either 0 or 1. So it means this f of x at the output is only one bit, either 0 or 1. So in this case, if I make this y 0, what this output would be? This would be 0 plus f of x is equal to f of x, and the overall output and input relation of the function I can write like this. So this will become okay, instead of this 0, so if this is 0, this becomes x f of x if this y is 0. And if this y is 1, this of course becomes 1 plus f of x. But let's work it out for a special input y, that what if y is a superposition of 0 and 1. So if this y is a minus state, and we can prepare this minus state very easily by passing 0 through the Hadamard. So if this y is the minus state, let's see what the output would be. So for x, y, which is equal to x 1 over under 2, 0, minus 1. And when this passes through the oracle, so these inputs, when they will pass through the oracle, x is going to be as it is. So this is 1 over square root 2. So this 0 will be transferred to 0 plus f of x, and the 1 will be transferred to 1 plus f of x. So I can further write it like this, that this will become x 1 over under 2, and this 0 plus f of x is nothing but f of x, and this 1 plus f of x is going to be minus 1. So this is this 1 plus f of x can be written as so it will depend on this thing. So but let's see it like this. So this should be 1 if f of x is 0, this will become x 1 over square root 2, 0 minus 1. Okay, so this is equal to x y again. So what if our f of x is 1? When f of x is 1, this will become x 1 over square root 2. This is 1, so this becomes 1. So this is 1. 1 plus 1 is 0. So 0. And I can take minus common. So this still becomes 0 minus 1, because when I take minus 1, this will become plus, this will become minus, and this is minus x y. So in general, I can write it like this, that this x y is transferred to minus 1 power f of x x y, because y doesn't change, y still remains y, x doesn't change, x still remains x, but it is being multiplied with this thing, that this sign is either plus or it is minus depending on f of x. So if f of x is 0, we get plus. If f of x is 1, we get minus. So it means in general, the role of this oracle is this, that it multiplies the output with this -1 f of x. And since this is a global phase, we can either think of it as with y or with x. And we can take it to work with x. So this then becomes like this. So let me now build a bigger black box. So this is called a phase oracle black box that have, some inputs coming from input x, and then inside this black box there is an amplitude oracle OF, which takes a qubit in the minus state and gives it at the output with minus state, but the x are now obtained like this, f of x into x. So this bigger black box, we can call it as some UF, and this now works like this. So if you have n input x, at the output you get -1 power f of x. So this one we call phase oracle because it adds a phase to the input. Okay, so the f of x that is implemented in this bigger oracle, which we are calling phase oracle, has to be implemented in such a way that the input is multiplied with -1 power f of x. And we'll see an example of this implementation in the notebook after this thing. But any question regarding the oracles? All right, if not, let's now get down to working the algorithm. So let me draw the circuit for the algorithm here again. We have Hadamards, and we have a phase oracle, and then we have the Hadamards, and then the measurements. Let's see if this can solve the dash problem or not. And we set up this circuit in such a way that the input is initialized to 0 state. So let me now see and pass through each step of this algorithm to see what it does. So I'll divide it into parallel steps. And let's say here the state is called psi naught, and here I'm going to label state as psi1, and here I'm going to label state psi2. Here I'm going to label state psi3. So let's work out this 0, psi naught, psi1, psi2, psi3, etc. So we are initializing this algorithm in such a way that the input state is this 0 state. Okay. And when it passes through this Hadamard transform, we have already worked out that what it should be. It is after n Hadamards on this input state, this will become 1/2n power 1/2 sum over all possible combinations of k. And with k, we don't need this -1 power kx term here because x is 0. This psi naught is all 0. So this becomes sum over k, and this -1 power 0 is 1. So this is k. So the state at this point, right after Hadamard, is this uniform superposition of all possible inputs. And that's actually where the quantum advantage comes, because now this phase oracle that we are going to feed with this input from this Hadamard transform actually has all possible combinations of inputs already. So let's see what happens at stage 2 right after the oracle. So psi2 is after we implement the oracle and psi1, and this is nothing but sum over n. So this oracle goes to this k states, and we get 2 power n, and this oracle is just implements this -1 power f of k, into k. Because this oracle is nothing but a phase oracle, that it adds a phase minus 1 power f of k to the input. Now let's see what happens after another Hadamard. So we have a Hadamard right after the oracle. So for this Hadamard, let's recall the formula that we have already worked out. So this is going to be 1 over 2n, sum over n minus 1 power f of k, and this Hadamard comes right to this state. So this we already know what it is. We just worked out. So 1 over 2n square root n minus 1 power f of k. This is sum over n and 1 over 2n square root minus 1 power sum L into k. Right? This is what we just worked out the Hadamard transform, that when n bit Hadamard transform works on this state, it is transformed to a superposition with the phase factors coming from this minus 1 power lk. Now, previously I was having this k as x state, and the sums were something k, but now it's being implemented on k. So I have introduced another variable L. So L is again the same thing. L goes from L0, 01, L1, 02, and so on. So this L are different possible states. Any question about this mathematics? I can combine these two square roots. And let me write, sorry, this sum is wrong. The sum is going to be over all not L. The sum is going to be over all N, because this is now the running index. So let's combine these two square root into 1 over 2n. And let me write this sum first, sum over L, and then minus 1 power f of k from here plus L into k into. So we have sum over L states, and the coefficients of these L states is given by this. Okay, so we are now almost to the final step, because now I can see what will happen. And let me call sorry, somehow the screen is collapsed. Sorry, my journal app has collapsed. I'm trying to restart it. Let's hope not much is lost. Okay, thankfully not a lot of stuff has lost, but let's see. All right, so we were here and we were working outside 3. So let's shift this sum over L to here, and we have this thing, sum over n minus 1 power f of k plus L. So this sum that I have written over n, this should actually have been the sum over k. Okay, because running state here is k, so index is k. So this is sum over k. So this sum is taken inside minus 1 power f of k plus lk into l. All right, so let me write it like this: 2n sum over l. Let's call all of this number sum cl, which is the coefficients of state l. So this is my psi3, where cl is this sum over k minus 1 power f of k plus l into k. Now let's work out one thing. What are the probabilities of different things? So let's first find out probability of finding state 3, psi3 in 0 state. At the output psi3, that if I measure it, what's the probability of it in the 0, 0, 0, 0, 0 state? So that I can work out easily. So this is the product, inner product of this state psi3 with state 0, 0, 0. This is the basis state 0, 0, 0. So if I want to find out the probability of measuring psi3 with 0, 0, 0, I have to find this inner product of psi3 with 0, 0 and take its absolute square. So this gives us the probabilities. So let's work out this number. So for this 0, 0, 0 into psi3 would be 1 over 2 power n sum over L CL into 0, 0, 0 L. Awesome. So I just multiply this state with 0, 0 from the left. Okay, so now this is 0, 0, 0, and this L is all states. First it is 0, 0, then it is 1, 1, and 1, 0, 0, and so on. So this inner product is non-zero only when this L is 0. So when L is 0, so this sum goes away, and we have C0, and this will then be 1. So this becomes square, and we can work out this, C naught as something. And this C naught actually I can find right away. This C naught is sum over k minus 1 power f of k plus k dot l, and my L is 0, so this becomes 0. So this is square. So since this L is 0, because it is 0, because for all other dot products, when L is not 0, this dot product is 0. So only the term is left with L is equal to 0. So from this part, this L is 0. All other states with L not 0 have been, dot product with an answer 0. So only this k into 0 is 0. So this will also go away, and I have 1 over 2n sum over k minus 1 power f of k into square. So let's now work out different cases. Suppose f of k is 0 for all k. That for all possible values of this combination k, this f of k is 0. It means that it's a constant function with output 0. So what would happen? Minus 1 power 0. So this will become 1. So if this is 1, so sum of 1 over k terms, where k goes, if I talk about, in decimal terms, it goes from 0 to 2n minus 1, because the total number of combinations of k are 2n. So this 1 summed over 2 power n times will give us 2 power n into 2 power n. So square, and this cancel, and we get 1. So it means if f of k is 0, this sum gives me 2 power n, and this cancels, and I get probability 1. Let's talk about another case. So f of k, if f of k is 1, then it is 1 for all k. That it is still a constant function, but no output is 1. So if f of k is 1, this minus 1 power 1 is minus 1. So now I'm going to sum minus 1 for 2 power n times. So I will get 1 over 2n with a minus sign. absolute square, which will also mean that 2n cancel with 2n, and I get -1 absolute square, and it becomes 1. So it means if your function is constant, your probability of measuring zero state is absolutely 1. So you will not measure any other state. Now let's see what happens if f of k is balanced. If f of k is 0 for half k and it is 1 for other half k, what would happen? Now you see this sum, when f of k is 0, I will get -1 power 0 as +1. And when this f of k is 1, I will get -1 power 1 as -1. So for half of the time in this sum, the situation is like this. So 1 over 2n, and it is 1 plus 1 plus 1, and then -1, -1, -1, -1. So for half of the k values, it's +1, and for the other half, it is -1. So the sum becomes 0, and this probability will be 0. So now I can sum it up. If I measure at the output here, if I measure my state psi3 and I get output 0, so this is 0, this is 0, all in outputs are 0, it has only one possibility, and that is that f of k was either 0 or 1, which means that it was a constant function. And if I don't measure 0, because the measuring of probability is 0 if f of k is balanced, so it means it is a balanced function. Is that okay? All right, so let me now show you the implementation on a quantum computer, but let me explain a couple of things again. So we have these inputs initialized to 0, and we have these Hadamard gates. We have this phase oracle, which is implemented with an amplitude oracle, and an Encilia qubit initialized to minus state. And then at the output, we have Hadamard, and then we have these measuring devices. So if you see, we are now saying that with just one query of this function, we are now able to measure whether function is a constant or balanced. So it means that we have an exponential speed up in reference to the solution of the problem. So this is a problem that classically requires n queries, which is 2 power n. So classically, quantum mechanically, I only require one query. So this is exponentially faster than 2 power n. The second thing is that how does quantum computer works it efficiently? It works because of this Hadamard transform, because I'm now able to transform a single input state into a superposition state that has all the possible inputs in it. And I'm able to pass that superposition state to this circuit. So all of this is quantum mechanical. So a quantum mechanical ability of processing superposition states essentially is giving us this probability, is this speed up, because we are able to access this phase oracle for all the possible combinations of input at the same time. So with just one query, we are able to get a state that when I take a Hadamard again and I measure it, I'm able to collapse it to a certain state that can give me a solution to the problem. Okay, so let me now show you how to implement it on a notebook, and maybe you can open your notebooks on your computers. I think I shared with you. This notebook. All right. So in the first part, you see I have this this, importing from Qiskit of quantum circuit, execute air, basic air, and this plot histogram that I will use to plot it. Now I am first of all building a quantum circuit which mimics an oracle, and for constant oracle, you see it's very easy to make. So I'm taking a random number, a 2-bit random number, and see if it is 1 or 0. If it is 1, I'm preparing a constant oracle and I'm implementing an X gate to this, because when these inputs Q0, Q1, Q2, so they have to be identical. So the oracle is just very simple, that whatever is at the input, the same thing is getting at the output. And with this X gate, this is this Q3 is my ancilia qubit that is not needed for working the actual program. It's just needed to work out the oracle. So when X is not used, so let's just start working it out. So when X is not implemented, I get a constant function with all outputs implemented with f of x0. So this is sort of trivial oracle. So it's constant because whatever is Q0, Q1, Q2, they're getting to the output as it is, and it is implementing f of x is equal to 0. So when f of x is 0, your input should be equal to output. X should go to x. So that's why the constant oracle with f of x is equal to 0 is very trivial. But the constant oracle with f of x is equal to -1, with f of x is equal to 1 should multiply your inputs with minus. But so how am I doing it? I'm keeping the inputs as it is, but I'm having the ancilia qubit as with an X gate, which flips the 0 into 1. So which is essentially equal to multiplying the input state with minus. And then I have a circuit for the balanced oracle. So, but a balanced oracle can be prepared in many ways. Okay, so for example, I'm starting one way of implementing it is that I implemented using the C0 gates. But before I implement the C0 gates, I'm preparing my ancilia qubit Q3 in minus state. And how I'm preparing in minus state? This this Q3 bit, which is initialized to 0, it's now with X gate, this becomes 1. And when I implement the Hadamard gate on this 1, this becomes the minus state. So with this minus state, when I implement a C0 gate, this is equivalent to adding a phase to this Q0 bit. So but before I do that, we have a choice. Let's say, let me make it actually simply 0, 1, 1, 1, 0, 1, but without the X gate. That will even be simpler. So let's not apply the X gates. And let's not apply the X gate in the beginning. So, okay, so there is these X gate. Let me remove these X gates and just keep the C0 gates. So you see, these two C0 gates essentially implements an oracle which adds a phase to the circuit if for some of the qubits, and doesn't do anything for other qubit combination. What you should do is actually work out the outputs for different combinations of the inputs and see for half of the inputs it is multiplying with minus, and for the other half it is multiplying with plus. And you can get different combinations of, let's say, placing X gates before or after. So they flip the bits that that give ones, and the bits that give -1. Okay, so in this case, it's another combination. So you can get even more combinations by selecting these C0 gates at different places, and also putting, but whenever, and you can put these X gates to flip those bits, but when you have to put an X gate, you also have to revert it, because the output should be equal to the input gates. So I would advise you actually to work out one bit by bit for different combinations of inputs to see that it really implements a balanced oracle. Okay, once we have all of this, I can combine this diet-Zosa circuit into one. So I start with implementing these Hadamard gates on each qubit, and then I have this just barrier for visualization, and then I combine this DJ circuit. I add this balanced oracle. You can add a constant oracle when you want, and then I add another barrier for visualization, and then I add these Hadamards at the end, and then another barrier for visualization, and at the end we have these measurements placed. So let me make this circuit. So this is the circuit in front of you. So these are the three Hadamards. So this Q3 is the ancilia bit. It's only used to prepare this oracle. It's not being used anywhere else. And then we have this oracle, and then Hadamards again, and then measurements. Now I'm going to show you its implementation on a simulator first, and then I will discuss how to you can run it on a quantum computer. So I'm using this COSM simulator, and so it is. So for 101, we are getting a probability of 1, but there's no state 00. It means that this is a balanced function, because we knew that when we used a constant oracle, we always measure 00, but other than that, we should measure any other state other than 0 is a balanced oracle. So let's see what happens with the constant oracle. So constant oracle is defined with const_. So let me now make this circuit. So I'm now implementing the same circuit but with a constant oracle. So let's run the simulator this time, and you see that now I'm measuring the state 00 with 1 probability. So it means that this is a constant oracle. So in this case, I actually already know what oracle I have implemented, but in a real problem, you can imagine that there is some black box function that implements this constant function. Okay, so let's see how you can implement it on a quantum computer. For that, let me go to the IBM account. So I hope all of you have already made an account there. And if you log in there, okay, so I have already logged in. And to run a program, what you need to do, you need to go to this front screen, and you have to copy your API token. So you press this button, and the token is copied. You can generate a fresh token by clicking it on here. And once you have that token, you can go to the notebook, and from Qiskit, you need to import this package IBM Cube, which contains commands to link your notebook with the IBM account. So now, so you can use this command IBM Q.save account, and then in the in these apostrophes, you have to put your token, and then always place this command overwrite is equal to true, that whatever is already written there in the token is get overwritten with this. So just to show you an example, the token that I just copied is exactly the same that I have already used here. So this is a token that connects me to my account. So I run it, and so this you have to do only once. Okay, I didn't have to do it this time, but I just did it for to show you. And then whenever you open your notebook again after closing it, you have to run this command, that IBM2 load account. So once you run this command, it loads your account, essentially loads this token into the system, that when you use your quantum computer, your account gets used. Now, to run the circuit on that computer, I will have to select a quantum computer. And for example, this time I have used this IBM2 Bellum computer. But you can go here and see what are other computers that are available. So you can go to here, your systems, and you can check. There are 8 system and 5 simulators that are available for me as a fair share account. But you can go here and check what are the other quantum computers that are available. So we can, instead of all, let's go to that are available to me. So there is this Santiago. This is a 5-qubit computer and its quantum volume is 32. Quantum volume is essentially measure of good qubits and how much, how many circuits they can run before they decoher. So a bigger quantum volume is the one that you need, is the one that will give you better results. So this is this one, and then there is this Athens computer. This is also 5-qubit, and this is also online. There's this Bellum computer. This is a 5-qubit, but this has a lower quantum volume, so that's why there's less traffic on it. Which means that if you run your program, you can run it easy. So this COSM simulator and state vector simulator we have already been using, but you can also use these simulators that for Clifford type quantum computing, and then there is this there are other simulators available as well. So let's go to this table where you can see. Okay, so if you come here, you can now see that how much busy different quantum computers are. For example, this Santiago has 1,489 jobs pending right now. So if you submit a job to it right now, it will take a lot of time before your turn comes in. So I'm using this Bellum because this is a bit noisy computer, but this has only 113 jobs pending. So if I run my command now, it will be ran pretty quickly. But I'll let me just run it and I'll show you what it's. There's this one, and so now it's being executed, but I have already run it to show you the result. So this is the result that I got from this Bellum quantum computer, and you can see that for the previous balanced circuit, when I had this 101, and in the simulator I had this probability 1 for 101 string, but here for the 101 string my probability is 0.697 only, and there are still other possibilities, which is because of the noise in the quantum computer. So but if you get a thing like this, you can pretty much assume that this 101 has the highest probability and all other states have low probability. So this is a trouble with quantum computers that are available right now to work for public, that the results are noisy, that the results that you expect from the quantum computer, they are not the one that you're going to receive when you actually run your program on a quantum computer. You will be getting outputs for other states as well. I think the rest of this notebook implements another algorithm, Bernstein-Vazirani, that we will discuss in the next class. But let me go to this account as well, where you can see what's going on with your notebook. For example, I have submitted this program which is still in queue, and if I want to go, I can close my notebook and go, but my program and everything is now saved here. Let's see if I go to my dashboard. And by the way, you can compose your circuit right here as well. Okay, you can launch a composer here. There's a graphical composer, and you can launch your Qiskit composer from here as well. So let's see, I have one pending job, and so it's going to show, let's see the jobs that I have completed. So for example, this is the recent job that I completed. So when you can log out and go when your job is executed, you can always come back here and see the results. So this is some other job that I had ran, but let me see some other job to show you. Okay, so these are the results that I was just showing you that I have obtained. So even when you log out your circuit, though your results are always available here that you can access. So this one is the one that I just submitted. Oh, this is already worked out, but this is not the one that I think I should have seen. Yeah, this is still working. Okay, so any questions? So what I would suggest to you is that you create your account and you can take a circuit from the ones that I have sent you and try to run it on IBM's account and see and play with it and try to build some other Oracle and then use that and run the program and try to interpret the results to get an experience of how to write and submit the jobs to IBM Q.
Assalamu alaikum, sir. I have a question.
Walaikum Assalam, Gigi.
Sir, how many shorts you mentioned while running this simulation? While this running on real quantum computer, it was almost 1024. Can you please share your Jupyter screen? I have a question about that.
Okay. So, okay.
Yeah, it's 1024 shorts.
Sorry, 102 what? Oh, okay. So this is, yes. So I ran it for 1024. There's no specific reason. I think you can go up to almost 8,000 shots.
Okay. So my question is, why, if I have to run it over for, let's say, 1,000 shots, how can I say that I obtain results in one iteration or in one loop instead? I can see that I have to run my simulation 1024 times, then I got the probabilistic results. However, in classical computer, I have to run for, let's say, if my function take 2 qubits, then I have to run it for 4 times. Then what is the superiority of quantum computer over simulation? Because I see I have to run quantum 1,000 times and simulation classical computer 4 times.
Excellent question. Excellent question. Okay, so this is right at the heart of the difference of quantum computers and classical computers. So quantum computers, even if, for example, this dice user circuit that I have built, I have said you need one query and you get a state whose measurement can tell you whether your function is, balanced or not, balanced or constant. So you need a lot of measurement just to guess the status. So where is the advantage? So the advantage comes in asymptotic element. For example, let's say you talk about a 10 bit input. So when you have a 10-bit input, it means that your possible inputs are 2 power 10. That is, close to a billion. And if you use a classical computer, you need at least 500 million queries. But now with a classical computer, you need only one query, but you might need to run the circuit maybe, let's say, 1,000,000 times. So still you get an advantage of 449 million times over classical computer. But if you just think about 1 bit or 2 bit, then of course classical computers are better. So quantum computers are better when you go to a few more than a few bits.
Sure, fine. Thank you. It's clear now.
So this is the trouble. So in quantum computers, usually our answer is in a superposition state. And to get the advantage over the classical system, if we are just interested in that superposition state, we have to have a size of the input which gives us, advantage that overcomes the disadvantage of measuring the circuit many times. Okay.
Okay, sir. Thanks.
Any other questions? If not, then hopefully we'll meet again tomorrow. Thank you.